In this video, we're going to prove the Urysohn metrization theorem. And this theorem says every regular space X with a countable basis is metrizable. So how are we going to go about proving this? Well, one way to show that a space is metrizable is to embed it in a space that we know has a metric that induces that topology. So our plan here is to embed X, our space X, which we know is second countable and is regular. And we're going to embed it into R omega with the product topology. And it can be shown that R omega with the product topology is metrizable. We're not going to do that here, but it's relatively straightforward. And we're going to split up this proof into multiple steps. Step one, we want to prove that there exists a countable collection, we'll call it f of n, of these functions. And let me say continuous, they're also continuous functions, such that any point x naught of x and a neighborhood u containing x, there's some n, and we'll just index it by the natural numbers because this is a countable collection. So there should be some n such that f of n on x naught is greater than 0, and f of n vanishes outside of u, which looks like this. So the image of u's complement should be constant on 0. So we want to show that such a collection exists. And what we're going to do is we're going to use the fact that there's a countable basis for this topology. So we say, let this collection B of n be a countable basis. And then we're going to construct functions based off of these basis sets. And the way we do that is we say for each pair of indices, n and m, where the closure of the basis set corresponding to n is contained in the basis set of m, and now we use Urysohn's lemma, which we showed in the last video, how to prove that. And Urysohn's lemma gives us a way of constructing a function that separates two disjoint closed sets in a space that's normal. And note that this space is also normal because every regular space with a countable basis is also normal. So we can use Urysohn's lemma here to build a function g, and it's going to be indexed by n followed by m, such that, and this is a map from x to 0 to 1, and we want g sub n and m to be equal to 1 inside the closure of B of n, which is our first disjoint closed set. So we have this function, the image of the closure of B of n is equal to 1, and it vanishes outside of B of m because the complement of an open set is a closed set, and since the closure of B of n is contained in B of m, it's a disjoint closed set from B of n. So we have also that the complement of B of m should map to 0. And this is a continuous function. Now we claim that this collection of functions is the desired countable collection. And this is pretty easy to prove. So what do we want? We want a countable collection of functions such that for any point of x and any neighborhood of that point, we have a function that maps our point x to some value greater than 0, and vanishes outside of our neighborhood. So take x naught belonging to x and u, which is a neighborhood of x naught. And we use the fact that B is a basis to find B of M containing x naught, where B of M is contained in U. And now we use the fact that we're working with a regular space to also find a B of N containing x naught, such that the closure of B of N is contained in B of M. And now G and M is the continuous function, the one that we were looking for. Let's just verify really quick that's true. So since x naught belongs to the closure of B of N, and the image of the closure of B of N is just 1, then the function evaluation at this point is greater than 0 because it's equal to 1. And then we want to make sure that outside U, this function vanishes, and the complement of U is contained in the complement of B of M, and we know that the image of the complement of B of M, by the way we define this function, is 0. So this just implies that the image of the complement of U is also 0. And that's good. So now we have our countable collection of continuous functions that meet the criteria we want. So we can choose any point now of our space X and any neighborhood containing that point, and we can find a continuous function such that its value on that point is greater than 0, and it vanishes outside that given neighborhood of the point. And now we can just, since this is indexed by the integers, or the positive integers, cross the positive integers, we know that this set is countable. So we can just re-index this by the integers alone. And now we have, for every integer we have, or for every positive integer, we have some continuous function that's going to meet our criteria for a given point in neighborhood. Step 2. Now that we've defined this countable collection of continuous functions, we take this collection, f of n, and define a larger function from all of x to r omega. So not just to r. And we're going to define it by the following rule, where for some x, at each coordinate we evaluate one of these functions in this collection. And the claim is that f is an embedding. So how do we show that f is an embedding? Well, we have to show, 1, that it's continuous, 2, it's injective, and 3, it's an open map onto its image. So we have to show these 3 things. And what this does is it essentially shows that f is a homeomorphism from x to a subspace of r omega, which is just the definition of an embedding. So firstly, we can prove continuity. Since each f of n, so each coordinate function, is continuous by the way we defined it, and r omega is given the product topology, f is therefore continuous. And this is not exactly trivial. I mean, there's a proof that this is the case when specifically you have the product topology on R omega, which is the countably infinite product of R, Cartesian product. But so we're not going to prove that here, but this is a theorem. And I spelled continuous wrong. Now, secondly, it's injective. So suppose x is not equal to y. Now, since the space is Hausdorff, we know that we can find an open set containing x, call it u, and some disjoint open set containing y, call it v. But then we can just choose x and u and say there's some n where f of n x is greater than 0, but the image of the complement of this set just maps to 0, so it vanishes. But then since these sets are disjoint, u and v is contained, well, y is an element of v, which is contained in x minus u, which implies that f of n on y evaluates to 0. So these two things are different. And if the entire function differs by at least one coordinate, then the whole function evaluation is different. So this function is injective. And lastly, we want to show that it's an open map onto its image. So the image of the entire space X, which we'll just call Z, which is some subset or some subspace of R omega. So we have to show that if we have an open set U of X, that f of u is open in Z with the subspace topology. And the plan to show this is we let Z naught be some point in the image of our open set f of u, and then we want to find an open set. We want to find an open set of Z, call it W, such that Z naught is an element of this open set, which is contained in f of u. And this is just showing that every point is an interior point, and we have an open set here. So what we're going to say is let x naught be the point of u such that f of x naught is equal to z naught. And we can do this just because, I mean, z naught comes from somewhere, so it's the image of some point. And let's say x naught is that point. And that point is unique because we have an injection. So now we choose n using our countable collection of these continuous functions such that f of n, x naught is greater than 0, and f of n on the complement of u vanishes. So now we want to define another open set. We're going to take this open interval in R and we want to define this open set in Z. We'll call it V, which is the reverse or the pre-image of this projection function from this open ray in R. So the way you can think about this is that this is all the points in R omega, so on, such that this nth coordinate is greater than 0, because these are all the points in R omega that are going to project to this open ray with this nth index projection. And now we let our open set W, which is the one we're trying to find, just be equal to the intersection of V and the image of f of x, which is just Z. So the claim is we need to show two things. Z naught is an element of W, and further, that W is contained in f of U. So firstly, we're going to show that Z naught is indeed an element of W, since the projection of Z naught is equal to the projection of f of x naught, because Z naught is f of x naught. But then the projection of this function with all these different coordinate functions is just the nth coordinate function, which is f of n x naught. And remember, we chose f of n to be such that on x naught, it's greater than 0. And since this is the case, we have that the projection of Z naught is an element of this open ray, and therefore Z naught is an element of V intersected with Z, which is W. So now the last thing is we want to show that W is contained in f of U. So let's take some arbitrary point of W. Let's say take Z as an element of W. Then again, we take this back into its pre-image, and we say that Z is some image of some point X for some X in our space. And we know that the projection of Z is contained in this open interval, since W is equal to V intersected with Z, so it needs to be in V, and V is just the pre-image of that open interval with this projection map. So we know that the projection of Z is going to map into this open ray. And now, since the projection of Z is equal to the projection of f of x, and it's kind of the same trick we did above, which is just equal to this coordinate function f of n on x, and we know that f of n vanishes outside U, so f of n on the complement of U is just constant on 0. But we know that f of n on x maps to something greater than 0, which implies that x must belong to U. But f of x is Z, so what that means is Z equals f of x belongs to f of U. And since we've shown now that Z belonging to W implies that Z belongs to f of U, we have shown that W is indeed contained in f of U. So this says that f is an open map onto its image, and therefore f is an embedding, and therefore we have shown that X is metrizable if it's has a countable basis and is regular. And we're done.